after William Morgan, Philip Keenan, and Edith Kellman, the astronomers based at the Yerkes Observatory in Wisconsin who formulated it. This system denotes luminosity with Roman numerals, although a few letters are also used. The advantage of the MKK system is that it gives a star a size as well as a temperature, so that stars can be described in colloquial terms such as white dwarf, red giant, or blue supergiant. The main sequence stars, including the Sun, are all small enough to be called dwarfs. The Sun is a G2V star, which indicates that it is a yellow dwarf with a surface temperature of about 5,800 K. Classes and characteristics. The hottest class of star, O-types, have a surface temperature in excess of 30,000 K. Most of the radiation these stars emit is in the ultraviolet part of the spectrum and appear blue when viewed in visible light. O stars are mainly giants, typically 20 times as massive as the Sun and 10 times as wide. Only 0.00003% of main sequence stars are this hot. O-type stars burn their fuel very quickly and release huge amounts of energy. As a result, they have a short life expectancy, which is measured in tens of millions of years, compared to billions for cooler stars. Members of this class have weak lines of hydrogen in their spectra, and strong evidence of ionized helium, which is present because of the high temperature. With a surface temperature of between 10,000 and 30,000 K, B-type stars are brighter in visible light than O-types, despite being cooler. This is because more of the radiation is emitted as visible light, making them blue-white. Again, B-type dwarfs are rare, making up less than 0.1% of main sequence stars. When they do occur, they are perhaps 15 times more massive than the Sun. B-type stars have non-ionized helium in their spectra and more evidence of hydrogen. Because they live for only a short time, B-type stars are found in molecular clouds or star-forming regions, since they have not had time to move far from the location in which they formed. About twice as large as the Sun, main sequence A-type stars have a surface temperature of between 7,500 and 10,000 K. They have strong hydrogen lines in their spectra and emit a wide spectrum of visible light, which makes them look white. As a result, they are some of the most easily seen stars in the night sky, and include Vega, Gamma Ursae Majoris, and Deneb. However, only 0.625% of main sequence stars are A-type stars. The prism has revealed to us something of the nature of the heavenly bodies, and the photographic plate has made a permanent record of the condition of the sky. Williamina Fleming. Cooling stars. As dwarf stars cool, the hydrogen in their spectra becomes less intense. They also exhibit more absorption lines due to metals. This is not because their composition is different from that of hotter stars but because the gas near the surface is cooler. In hotter stars, the atoms are too ionized to create absorption lines. F-type stars have a surface temperature of between 6,000 and 7,500 K, called yellow-white dwarfs. They make up 3% of the main sequence and are a little larger than the Sun. The spectra of these stars contain medium-intensity hydrogen lines and strengthening lines for iron and calcium. The strengths of the absorption lines of different elements vary according to the surface temperature of the star. Lines of heavier elements are more prominent in the spectra of cooler stars. The Sun's class. Type G yellow dwarfs, of which the Sun is one, make up 8% of the main sequence. They are between 5,200 and 6,000 K on the surface and have weak hydrogen lines in their spectra, with more prominent metal lines. Type K dwarfs are orange and make up 12% of the main sequence. They are between 3,700 and 5,200 K on the surface and have very weak hydrogen absorption lines but strong metallic ones, including manganese, iron, and silicon. Type M are red dwarfs. These are by far the most common main sequence stars, making up 76% of the total, although no red dwarf is visible to the naked eye. They are just 2,400, 3,700 K on the surface and their spectra contain absorption bands for oxide. Compounds. The majority of the yellow, orange, and red dwarfs are believed to have planetary systems. A white dwarf sits at the heart of the Helix planetary nebula. When its fuel ends, the Sun will become a white dwarf. Extended classification. Stellar spectral classes now cover even more types of stars. Class W are thought to be dying supergiant stars. Class C, or carbon stars, are declining red giants. Classes L, Y, and T are a diminishing scale of colder objects, from the coolest red dwarfs to the brown dwarfs, which are not quite large or hot enough to be classed as stars. Finally, white dwarfs are Class D. These are the hot cores of red giant stars that no longer burn with fusion and are gradually cooling. Eventually they should fade to black dwarfs, but it is estimated it will take a quadrillion years for that to happen. Annie Jump Cannon. Born in Delaware, Annie Jump Cannon was the daughter of a state senator, and was introduced to astronomy by her mother. She studied physics and astronomy at Wellesley College, an all-women's college. Graduating in 1884, Cannon returned to her family home for the next 10 years. On the death of her mother, in 1894, she began to teach at Wellesley and joined Edward C. Pickering's Harvard Computers 2 years later. Cannon suffered from deafness, and the ensuing difficulties in socializing led her to immerse herself in scientific work. She remained at Harvard for her entire career, and is said to have classified 350,000 stars over 44 years. Subject to many restrictions over her career due to her gender, she was finally appointed a member of the Harvard faculty in 1938. In 1925, she became the first woman to be awarded an honorary degree by Oxford University. Key work. 1918, 24 The Henry Draper Catalog. See also, the Sun's Spectrum Analyzing Starlight, the Sun's Emissions, the Star Catalog Analyzing Absorption Lines, Refining Star Classification, Stellar Composition. In context. Key astronomer. Ejnar Hertzsprung. Before 1866, Angelo Secchi creates the first classification of stars according to their spectral characteristics. 1880s, at the Harvard College Observatory, Edward Pickering and Williamina Fleming establish a more detailed classification system. 1890s, Antonia Mori develops her own system for classifying star spectra, taking into account differences in width and sharpness of spectral lines. After 1913, Henry Norris Russell creates a diagram, similar to one made by Hertzsprung, that plots the absolute magnitude of stars against spectral class. This later becomes known as a Hertzsprung-Russell diagram. In the late 19th and early 20th centuries, Edward Pickering and his assistants carried out extensive work classifying star spectra. They catalogued the range of light wavelengths coming from a star, which, among other information, contains dark absorption lines. These lines indicate the presence of particular elements in the star's atmosphere that are absorbing those wavelengths. One of Pickering's assistants, Antonia Mori, developed her own classification system, taking into account differences in the width of absorption lines in star spectra. She noticed that some spectra, which she denoted as C, had sharp, narrow lines. Using Mori's system, Danish astronomer Ejnar Hertzsprung saw that stars with C-type spectra were far more luminous than other stars. Bright and dim red stars. Hertzsprung figured out that what Mori had identified as C-type stars were radically different from other types in the same category. For example, within the M-class category, or red-colored stars, he noticed that the C-types were highly luminous, high-mass. Comparatively rare stars, today, these are called red giants or red supergiants, depending on their size. The remaining majority of non-C-type M-class stars were low-mass, faint stars that are now known as red dwarfs. A similar distinction of two main kinds also applied to K-class stars. A typical red giant has a diameter about 50 times that of the Sun, and 150 times that of a typical red dwarf. However, a red giant has only about 8-10 times the mass of a red dwarf. See also, the Sun's Spectrum Analyzing Starlight, the Star Catalog, the Characteristics of Stars, Refining Star Classification. In context. Key astronomer. George Ellery Hale. Before 800 BCE, the appearance of dark spots on the Sun is recorded in the Chinese Book of Changes. 1600, English physicist William Gilbert discovers that Earth has a magnetic field. 1613 Galileo demonstrates that sunspots are features on the surface of the Sun. 1838 Samuel Heinrich Schwab notes a cycle in the numbers of sunspots seen each year. 1904 British astronomers Edward and Annie Maunder publish evidence of an 11-year sunspot cycle. After 1960 U.S. physicist Robert Layton introduces the field of helioseismology, a study of the motion of the solar surface. American George Hale was just 14 when his wealthy father bought him his first telescope, and 20 when his father built him an observatory on the family property. 2 years later, while at MIT, Hale developed a new design for a spectroheliograph, a device for viewing the surface of the Sun one wavelength of light at a time. He used this device to study the spectral lines of sunspots. Some years later, Hale organized the building of some of the largest telescopes in the world at the time, including the 60-inch Hale telescope, built at California's Mount Wilson Observatory in 1908, paid for by a bequest from his father. Working at Mount Wilson that same year, Hale was able to take clear images of sunspots in a deep red wavelength emitted by hydrogen. The speckled images reminded Hale of the way iron filings mapped the force field around a magnet. This led him to look for signs of the Zeeman effect in light coming from the sunspots. The Zeeman effect is a split in spectral lines caused by the presence of a magnetic field, first observed by the Dutch physicist Peter Zeeman in 1896. The spectral lines in light coming from sunspots had indeed been split, which suggested to Hale that sunspots were swirling magnetic storms on the surface of the Sun. The variations in the strength of the Sun's magnetic field are shown in this magnetogram, produced using the Zeeman effect. The marks correspond to the locations of sunspots. See also, Galileo's telescope, the surface of the Sun's vibrations. Maunder. In context. Key astronomer Henrietta Swan Leavitt. Before 1609 German pastor David Fabricius discovers the periodically variable star Mira. 1638 Dutch astronomer Johannes Halwarda observes Mira's variation in brightness over a regular 11-month cycle. 1784 John Goodricke discovers a periodic variation in the star Delta Cephei, the prototypic example of a Cepheid variable. 1838 Friedrich Bessel measures the distance to the star 61 Cygni using the parallax method. After 1916 Arthur Eddington studies why Cepheids pulsate. 1924 Edwin Hubble uses observations of a Cepheid in the Andromeda Nebula to calculate its distance. Some of the most important, but often most challenging, measurements for astronomers to make have been the distances to extremely remote objects, which includes most celestial objects aside from the Moon, Sun, and other planets of the inner solar system. Nothing in the light coming from distant stars and galaxies gives any direct indication of how far that light has traveled through space to reach Earth. For several hundred years, scientists realized that it should be possible to measure the distances to relatively nearby stars by a method called parallax. This is based on comparing the position of a nearby star against the background of more distant stars from two perspectives, usually Earth's different positions in space 6 months apart in its orbit around the Sun. Although many others had tried before him, the first astronomer to measure a star's distance accurately using this method was Friedrich Bessel, in 1838. However, even with increasingly powerful telescopes, measuring star distances by parallax proved difficult and, by the year 1900, the distances to only about 60 stars had been measured. Furthermore, the parallax method could be applied only to nearby stars. The difference in perspective for more distant stars over the course of a year was too small to be accurately determined. New methods were therefore needed to measure large distances in space. A remarkable relation between the brightness of these variables and the length of their periods will be noticed. Henrietta Swan Leavitt. Measuring brightness. In the 1890s and early 1900s, the Harvard College Observatory in Massachusetts was one of the world's leading astronomical research institutions. Under the supervision of its director, Edward C. Pickering, the observatory employed many men to build equipment and take photographs of the night sky, and several women to examine photographic plates taken from telescopes throughout the world, measure their brightness, and perform computations based on their assessment of the plates. These women had little chance to do theoretical work at the observatory, but several of them, including Williamina Fleming, Henrietta Swan Leavitt, Antonia Mori, and Annie Jump Cannon, nevertheless left a lasting legacy. Henrietta Swan Leavitt, who had originally joined the observatory as an unpaid volunteer in 1894, eventually became the head of the photographic photometry department. This mainly involved measuring the brightness of stars, but a specific aspect of Leavitt's work was to identify stars that fluctuate in brightness, known as variable stars. To do this, she would do a comparison of photographic plates of the same part of the sky, made on different dates. Occasionally she would find a star that was brighter on different dates, indicating that it was a variable. One of the most striking accomplishments of Miss Leavitt was the discovery of 1,777 variable stars in the Magellanic Clouds. Solon I. Bailey, colleague of Leavitt. The Cepheid variable stars that Leavitt studied are in the Magellanic Clouds, known today to be galaxies outside the Milky Way. The Large Magellanic Cloud is about 160,000 light-years away, the Small Magellanic Cloud is about 200,000 light-years away. Both are part of the local group galaxy cluster that includes the Milky Way. Cluster variables. A specific task that Leavitt took on was to examine some of the photographic plates of stars in the Small Magellanic Cloud and the Large Magellanic Cloud. At the time, the SMC and LMC were thought to be very large star clusters within the Milky Way, which itself was assumed to comprise the entire universe. Today, they are known to be relatively small, separate galaxies that lie outside the Milky Way. The Magellanic Clouds are visible to the naked eye in the night sky of the southern hemisphere, but are never visible from Massachusetts, where Leavitt lived and worked. Therefore, although she examined numerous photographic plates of the LMC and SMC obtained by astronomers at an observatory in Peru, it is highly unlikely that she ever physically observed them in the sky. After several years' work, Leavitt had found 1,777 variables in the SMC and LMC. One particular kind that caught Leavitt's attention, representing a small fraction of all the variables she had found, was of a type called a Cepheid variable. Leavitt called them cluster variables. The term Cepheid variable was introduced later. These are stars that regularly vary in brightness with a period that could be anything from 1 to more than 120 days. Cepheid variables are reasonably easy to recognize because they are among the brightest variable stars, and they have a characteristic light curve, showing fairly rapid increases in brightness followed by a slower tailing off. Today, they are known to be giant yellow stars that pulsate, varying in diameter as well as brightness over their cycles, and are very rare. As a class of stars, they also have an exceptionally high average brightness, which means they stand out even in other galaxies. In examining her records of Cepheid variables in either the LMC or SMC, Leavitt noticed something that seemed significant. Cepheids with longer periods seemed to be brighter on average than those with shorter periods. In other words, there was a relationship between the rate at which Cepheids blinked and their brightness. Furthermore, Leavitt correctly inferred that, since the Cepheids she was comparing were all in the same distant nebula, they were all at much the same distance from Earth. It followed that any difference in their brightness as viewed from Earth was directly related to differences in their true or intrinsic brightness. This meant there was a definite relationship between the periods of Cepheid variables and their average intrinsic brightness or their optical luminosity. Leavitt published her initial findings in a paper that first appeared in the Annals of the Astronomical Observatory of Harvard College in 1908. Then, in 1912, after further study, which included plotting graphs of the periods of Cepheid variables in the SMC against values for their minimum and maximum brightness, she confirmed her discovery in more detail. It became known as the period-luminosity relationship. Formally, it stated that the logarithm of the period of a Cepheid variable is linearly related to the star's average measured brightness. A straight line can readily be drawn among each of the two series of points corresponding to maxima and minima, thus showing that there is a simple relation between the brightness of the variables and their periods. Henrietta Swan Leavitt. A Cepheid variable belongs to a class of star called a pulsating variable. These stars expand and contract over a regular cycle, at the same time regularly varying in brightness. They are hottest and brightest shortly after reaching their most contracted phase. The graph of the star's luminosity against time is called its light curve. Building on Leavitt's work. Although it is possible that Leavitt did not realize the full implications right away, she had discovered an extremely valuable tool for measuring distances in the universe, far beyond the limitations of parallax measurements. Cepheid variables were to become the first standard candles, a class of celestial objects that have a known luminosity, allowing them to be used as tools to measure vast distances in space. One of the first people to appreciate the significance of Leavitt's discovery was Danish astronomer Ejner Hertzsprung. Due to the period luminosity relationship discovered by Leavitt, Hertzsprung realized that by measuring the period of any Cepheid variable it should be possible to determine its luminosity and intrinsic brightness. Then, by comparing its intrinsic brightness to its apparent magnitude, it should be possible to calculate the distance to the Cepheid variable. In this way, it should also be possible to determine the distance to any object that contained one or more Cepheid variable star. However, there was still a problem to be solved. Although Leavitt had established the important period-luminosity relationship, initially all this promised was a system for measuring the distance to remote objects relative to the distance to the SMC. The reason for this is that Leavitt had no accurate information about the distance to the SMC, nor indeed any accurate data about the intrinsic brightness of any Cepheid variable. I should be willing to pay 30 cents an hour in view of the quality of your work, although our usual price, in such cases, is 25 cents an hour. Edward C. Pickering. Calibrating the variables. To turn Leavitt's finding into a system that could be used to determine absolute distances, not just relative distances, it needed calibrating in some way. In order to do this, it would be necessary to measure accurately the distances to an intrinsic brightness of a few Cepheid variables. Hertzsprung therefore set about determining the distances to a handful of Cepheids in the Milky Way galaxy, using an alternative complex method called statistical parallax, which involves calculating the average movement of a set of stars assumed to be at a similar distance from the Sun. Having obtained the stars' distances, it was a straightforward step to figure out the intrinsic brightness of each of the nearby Cepheids. Hertzsprung used these values to calibrate a scale, which allowed him to calculate the distance to the SMC and the intrinsic brightness of each of Leavitt's Cepheids in the SMC. Following these calibrations, Hertzsprung was able to establish a system for determining the distance to any Cepheid variable from just two items of data, its period and its apparent magnitude. Leavitt left behind a legacy of a great astronomical discovery. Solon I. Bailey. Further applications. It was not long before Leavitt's findings, tuned by the work of Hertzsprung, led to further important results in terms of helping to understand the scale of the universe. From 1914 to 1918, the American astronomer Harlow Shapley was one of the first to use the newly developed concept that the distances of variable stars could be found from knowing their periods and apparent brightness. Shapley found that objects called globular star clusters, all part of the Milky Way, were distributed roughly in a sphere whose center lay in the direction of the constellation of Sagittarius. He was able to conclude from this that the center of the Milky Way galaxy is at a considerable distance in the direction of Sagittarius and that the Sun is not, as had previously been supposed, at the center of the galaxy. Shapley's work, which led to the first realistic estimate of the true size of the Milky Way, was an important milestone in galactic astronomy. Right up to the 1920s, many scientists maintained that the Milky Way galaxy was the whole universe. Although there were those that believed otherwise, neither side could conclusively prove their argument one way or another. In 1923, however, the American astronomer Edwin Hubble, using the latest in telescopic technology, found a Cepheid variable in the Andromeda Nebula, allowing its distance to be measured. This led directly to the confirmation that the Andromeda Nebula is a separate large galaxy outside the Milky Way. Later, Cepheids were similarly used to show that the Milky Way is just one of a vast number of galaxies in the universe. The study of Cepheids was also employed by Hubble in his discovery of the relationship between the distance and recessional velocity of galaxies, leading to confirmation that the universe is expanding. The star Rs Puppis is one of the brightest Cepheid variables in the Milky Way. It is about 6,500 light-years from Earth and has a cycle of variability lasting 41.4 days. Revising the scale. In the 1940s, the German astronomer Walter Baade was working at the Mount Wilson Observatory in California. Baade made observations of the stars at the center of the Andromeda Galaxy during the enhanced viewing conditions afforded by the wartime blackout. He distinguished two separate populations, or groups, of Cepheid variables that have different period, luminosity relationships. This led to a dramatic revision in the extragalactic distance scale. For example, the Andromeda Galaxy was found to be double the distance from the Milky Way that Hubble had calculated. Baade announced his findings at the International Astronomical Union in 1952. The two groups of Cepheids became known as classical and type II Cepheids, and started to be used for different purposes in distance measuring. Today, classical Cepheids are used to measure the distance of galaxies out to about 100 million light-years, well beyond the local group of galaxies. Classical Cepheids have also been used to clarify many characteristics of the Milky Way galaxy, such as its local spiral structure and the Sun's distance from the plane of the galaxy. Type II Cepheids have been used to measure distances to the galactic center and globular clusters. The measurement of distances to Cepheid variables for more accurate calibration of period, luminosity relationships is still considered extremely important, and it was one of the primary missions of the Hubble Space Telescope project when it was launched in 1990. A better calibration is crucial, among other things, to calculate the age of the universe. Leavitt's findings from over a century ago are still having significant repercussions in terms of truly understanding the scale of the cosmos. Hubble's underwhelming acknowledgement of Leavitt is an example of the ongoing denial and lack of professional and public recognition that she suffers from, despite her landmark discovery. Pangratio's Papacosta, science historian. A simplified version of the mechanisms that cause Cepheid variables to fluctuate in size is shown here. The pressure forces inside a star include gas pressure, maintained by heat output from the star's core, and radiation pressure. Another mechanism that may be involved is a cyclical change in the opacity in gas within the star's outer layers. Henrietta Swan Leavitt. Henrietta Swan Leavitt developed an interest in astronomy while studying at Radcliffe College, Cambridge, Massachusetts. After graduation, she suffered a serious illness that caused her to become increasingly deaf for the rest of her life. From 1894 to 1896 and then again from 1902, she worked at Harvard College Observatory. Leavitt discovered more than 2,400 variable stars and 4 novae. In addition to her work on Cepheid variables, Leavitt also developed a standard of photographic measurements, now called the Harvard Standard. Due to the prejudices of the day, Leavitt did not have the chance to use her intellect to the fullest, but she was described by a colleague as possessing the best mind at the observatory. She was remembered as hardworking and serious-minded, little given to frivolous pursuits. Leavitt worked at the observatory until her death from cancer in 1921. Key work: 1908–1777 Variables in the Magellanic Clouds. See also, a new kind of star, stellar parallax, the star catalog, analyzing absorption lines, nuclear fusion within stars beyond the Milky Way space telescopes. In context. Key astronomer: Henry Norris Russell. Before 1901, Annie Jump Cannon, working at the Harvard College Observatory, introduces the star spectral classes O, B, A, F, G, K, and M. 1905, based on analyses of star spectra, Ejner Hertzsprung states that there are two fundamentally different kinds of star within some spectral classes, one of which is far more luminous. After 1914, Walter Adams discovers white dwarf stars, white-hot but relatively faint. 1933, Danish astronomer Bengt Stromgren introduces the term Hertzsprung, Russell diagram, to denote a plot of the absolute magnitudes of stars against spectral class. Around 1912, American Henry Russell began comparing stars' absolute magnitude and their color, or spectral class. Before the early 20th century, no one had figured out how different star types might be related in some overall scheme, but it had long been recognized that they differ in certain properties, such as color. While some stars shine with a pure white light, others have distinct colors. Many have reddish or bluish hues, while the sun is yellow. In 1900, German physicist Max Planck worked out the precise mathematics to describe how the mix of wavelengths of light given off by hot objects, and hence their color, varies according to their temperature. Thus, star colors are related to surface temperature. Red stars have the coolest surfaces, and blue stars the hottest. By around 1910, stars were considered to fit into spectral classes related to their colors and surface temperatures. The other obvious way in which stars differ is in their brightness. Since ancient times, stars have been classified into brightness classes. This developed into the apparent magnitude scale, which rated stars according to how bright they look from Earth. However, it was realized that, in order to know a star's absolute brightness, it would be necessary to correct for its distance from Earth. The farther away a star is, the dimmer it will appear. From the mid-19th century, reasonably precise distances to some stars began to be calculated, and the absolute brightness of these stars could be established. Russell's discovery. Among the majority of stars, Russell found a definite relationship. Hot blue-white stars tend to have higher absolute magnitudes than cooler white and yellow stars, while white and yellow stars have higher absolute magnitudes than orange and red stars. However, some exceptionally bright red, orange, and yellow stars departed from this rule. These were the giant stars. Russell plotted the absolute magnitudes of stars against their spectral classes on a scatter diagram, which he published in 1913. However, unknown to him, Danish chemist and astronomer Ejner Hertzsprung had performed a similar exercise a couple of years earlier, and the diagram is now known as the Hertzsprung-Russell diagram. The diagram shows stars divided into a group of bright giant stars and a much larger group of ordinary stars running diagonally. Russell called these ordinary stars dwarfs. Hertzsprung referred to them as main sequence. The newly discovered hot but faint white dwarfs were later added to the diagram, forming a third group. Today, it is known that most stars spend most of their lives on the main sequence, some later evolving into giants or supergiants. The Hertzsprung-Russell diagram shows the distribution of stars by absolute magnitude and spectral class. The diagram formed the basis for developing theories about how stars evolve. Henry Norris Russell. Henry Norris Russell was born in Oyster Bay, Long Island, in 1877. At age 5, his parents encouraged him to observe a transit of Venus across the Sun's disk, which inspired an interest in astronomy. He was awarded a doctoral degree by the Astronomy Department of Princeton University for an analysis of the way that Mars perturbs the orbit of the asteroid Eros. From 1903 to 1905, he worked at the Cambridge Observatory, England, on star photography, binary stars, and stellar parallax. In 1905, he was appointed as an instructor in astronomy at Princeton University, and in 1911, he became professor of astronomy there. He was also director of Princeton University Observatory from 1912 to 1947. Key works: 1927 Astronomy, a revision of Young's Manual of Astronomy, Volume 1, The Solar System, Volume 2, Astrophysics and Stellar Astronomy. 1929 On the Composition of the Sun's Atmosphere. See also, Analyzing Starlight, the Characteristics of Stars, Analyzing Absorption Lines, Measuring the Universe, Discovering White Dwarf Stellar Composition. In context. Key astronomer Victor Hess. Before 1896 French physicist Henri Becquerel detects radioactivity. 1909 German scientist Theodor Wolff measures air ionization near the top of the Eiffel Tower. Levels are higher than expected. After 1920s American physicist Robert Millikan coins the term cosmic ray. 1932 American physicist Carl Anderson discovers the positron in cosmic rays. 1934 Walter Baade and Fritz Zwicky propose the idea that cosmic rays come from supernova explosions. 2013 data from the Fermi Space Telescope suggest that some cosmic rays come from supernova explosions. Austrian-born physicist Victor Hess made a series of dangerous high-altitude ascents over eastern Germany in a hydrogen balloon in the years 1911 and 1912. His goal was to measure air ionization at a height of 3 miles. Ionization is the process by which electrons are stripped from atoms. In the early years of the 20th century, scientists were puzzled by the levels of ionization in Earth's atmosphere. After the discovery of radioactivity in 1896, it was suggested that ionization was caused by radiation emitted by substances in the ground, meaning that air ionization should decrease with altitude. However, measurements made at the top of the Eiffel Tower in Paris in 1909 indicated a higher level of ionization than expected. Hess's results showed that ionization decreased up to an altitude of about half a mile, and then increased above that point. He concluded that powerful radiation from space was penetrating and ionizing the atmosphere. This radiation later became known as cosmic rays. In 1950, scientists found that cosmic rays consisted of charged particles, some possessing very high energies. They smash into atoms in the atmosphere, creating new subatomic particles that may themselves create collisions, which in turn cause a cascade of collisions called a cosmic ray shower. In 1951, the Crab Nebula was found to be a major source of cosmic rays. Since then, supernovae and quasars have also been identified as sources, see also, supernovae. In context. Key astronomer Walter Adams. Before 1783 William Herschel discovers 40 Eridani B and C. 1910 Williamina Fleming answers an inquiry from Henry Norris Russell about the spectrum of 40 Eridani B, confirming that it is a Type A star. After 1926 British astronomer Ralph Fowler applies new ideas in quantum physics to explain the nature of the extremely dense material in white dwarfs. 1931 Subramanian Chandrasekhar calculates that white dwarfs cannot be more massive than 1.4 times the mass of the Sun. 1934 Walter Baade and Fritz Zwicky suggest that stars too massive to become white dwarfs form neutron stars. In the first decade of the 20th century, American astronomer Walter Adams developed a method for calculating the absolute magnitude of stars from the relative intensities of particular wavelengths in their spectra. One of the original team members at the Mount Wilson Observatory in California, Adams used his method to investigate the triple star system 40 Eridani, which contained a mysterious star that seemed very dim but also very hot. White dwarf. The brightest of the three stars, 40 Eridani A, was being orbited by a much dimmer binary pair, 40 Eridani B and C. Stars as faint as 40 Eridani B and C were expected to be of spectral class M, meaning that their starlight is red, indicating a relative coolness. 40 Eridani C fitted this profile, but 40 Eridani B was one of the whitest and hottest types of star. When Adams published the data in 1914, astronomers were presented with a puzzle: a star that hot had to be getting its energy from somewhere. The answer could only be that, although it was small, its density must be immense, about 25,000 times that of the Sun. 40 Eridani B was the first white dwarf star to be discovered. White dwarfs were later shown to be the hot stellar cores left behind when main sequence stars run out of fuel for nuclear fusion. Composed of material 3,000 times denser than anything you have ever come across, a ton of material would be a little nugget that you could put in a matchbox. Arthur Eddington describing white dwarfs. See also, Observing Uranus, Refining Star Classification, The Life Cycles of Stars, Energy Generation. Introduction. Despite the vast difference in scale, atoms, stars, and galaxies share a property in common: each in its own size domain is a fundamental construction unit of the universe. Galaxies define the distribution of matter in the universe on the grandest scale. Stars are a defining constituent of those galaxies. Atoms are the units of matter that make up the hot gas of stars. If we think of galaxies as cities, stars are like individual buildings within the city, and atoms are the bricks. In a mere 30-year period in the first half of the 20th century, astronomy took huge leaps in understanding how the hierarchy of matter in the universe is organized. Underpinning these developments was Einstein's general theory of relativity, in which the concepts of mass and energy are inseparable in a unified fabric of space and time. Looking inside a star. Between 1916 and 1925, Briton Arthur Eddington worked on the physical nature of ordinary stars such as the Sun. He pieced together a detailed physical description of a sphere of hot gas, in which energy makes its way from a central source to the surface, from where it then radiates into space. Eddington also did much to convince astronomers that stars are fueled by subatomic processes, what we would now call nuclear energy. In 1919, the New Zealand physicist Ernest Rutherford was able to transmute atoms of nitrogen into oxygen by firing particles at them from a radioactive element. There was now ample evidence that nuclear processes could produce new elements and release unimaginable quantities of energy. For any remaining doubters, Eddington reflected on the experiments conducted at Cambridge University by pointing out that what is possible in the Cavendish laboratory may not be too difficult in the Sun. When British astronomer Cecilia Payne-Gaposchkin, working in the US, concluded in 1925 that stars are overwhelmingly made of hydrogen atoms, astronomers at last had a real grasp on the true nature of ordinary stars. However, not all stars are quite so ordinary. White dwarfs, for example, are clearly extraordinarily dense. In the 1930s, the tools of the new quantum physics were used to explain how a star could become so compacted and predicted even more exotic types of collapsed star. It turned out that 1.46 solar masses would be the upper limit to make a white dwarf, but there was nothing to stop more massive stars from collapsing into a much denser neutron star or a black hole. Black holes may be real. Walter Baade and Fritz Zwicky speculated that the central remnant of a supernova explosion would be a neutron star, and with the work of Indian Subramanian Chandrasekhar and others, the theoretical concept of black holes was born, although many astronomers found it hard to believe they could really exist. In any event, it was 4 decades before the first neutron stars and candidate black holes were identified. The universe of galaxies. Meanwhile, the whole concept of the nature of the universe was changing rapidly. In 1917, American Vesto Slipher recognized that many so-called nebulae were galaxies, akin to our own Milky Way, and in rapid motion. Some 10 years later, Belgian priest Georges Lemaitre realized that an expanding universe was consistent with Einstein's theory of relativity. American Edwin Hubble discovered that the more distant a galaxy, the faster it is receding from us, and Lemaitre suggested that the universe began by exploding from a tiny, primeval atom like a firework. In just a handful of years, astronomers had learned that the universe was far larger and more complex than they had ever imagined. We used to think that if we knew 1, we knew 2, because 1 and 1 are 2. We are finding that we must learn a great deal more about and Arthur Eddington. In context. Key astronomer Albert Einstein. Before 1676 Ole Romer shows that light speed is not infinite. 1687 Isaac Newton publishes his laws of motion and universal law of gravitation. 1865 James Clerk Maxwell shows that light is a wave moving through an electromagnetic field at a constant speed. After 1916 Karl Schwarzschild uses Einstein's equations to show how much matter warps space. 1919 Arthur Eddington provides evidence for the warping of spacetime. 1927 Georges Lemaitre shows that a relativistic universe can be dynamic and constantly changing, and proposes the Big Bang theory. Albert Einstein's general theory of relativity has been called the greatest act of thought about nature ever to take place in a person's head. It explains gravity, motion, matter, energy, space and time, the formation of black holes, the Big Bang, and possibly dark energy. Einstein developed the theory over more than a decade at the start of the 20th century. It went on to inspire Georges Lemaitre, Stephen Hawking, and the LIGO team, which searched for the gravitational waves predicted by the theory. The theory of relativity arose from a contradiction between the laws of motion described by Isaac Newton and the laws of electromagnetism defined by Scottish physicist James Clerk Maxwell. Newton described nature in terms of matter in motion governed by forces that act between objects. Maxwell's theories concerned the behavior of electric and magnetic fields. Light, he said, was an oscillation through these fields, and he predicted that the speed of light was always constant, regardless of how fast the source was moving. Measuring the speed of light is not an easy thing to do. Danish astronomer Ole Romer tried in 1676 by measuring the time delay in the light arriving from Jupiter's moons. His answer was 25% too slow, but he did show that light speed was finite. By the 1850s, more accurate measurements had been made. However, in a Newtonian universe, there must also be changes in the speed of light to account for the relative motion of its source and observer. Try as researchers might, no such differences could be measured. At the end of the 19th century, many believed that physicists had fully figured out the laws of the universe. All that was now needed were more precise measurements. However, even as a child, Einstein was not convinced that physics had been solved. At the age of 16, he asked himself a question: what would I see if I were sitting on a beam of light? In the Newtonian context, young Albert would be traveling at the speed of light. Light coming from in front would reach his eyes at twice the speed of light. When looking back, he would see nothing at all. Even though light from behind was traveling at the speed of light, it could never catch up. Annus Mirabilis. Einstein's first job was working as a patent clerk in Bern, Switzerland. It afforded him a lot of spare time to devote to private study. The fruit of this solitary work was the Annus Mirabilis of 1905, when he presented 4 papers. These included 2 linked discoveries, special relativity and the equivalence of mass and energy, summed up by the equation E equals mc. Inside the speeding train, Bob shines a light beam directly up and down. Bob measures the time it takes for the light to be reflected back to him as the distance straight up and down divided by c. On the platform, Pat observes the beam traveling diagonally. It is still traveling at the same speed c, so more time must have passed than for Bob as the light has traveled a longer distance. Special relativity. Einstein used thought experiments to develop his ideas, the most significant of which involved 2 men, one on a speeding train and the other standing on the platform. In one version, inside the train, Bob shines a flashlight at a mirror directly above him on the ceiling. He measures the time the light takes to travel to the mirror and back. At the same time, the train is passing the platform at close to the speed of light. From the platform, the stationary observer Pat sees the light beam shine to the mirror and back, but in the time it takes for the beam to travel, the train has moved, meaning that, rather than traveling straight up and down, the beam travels diagonally. To Pat on the platform, the light beam has traveled farther, so, since light always travels at the same speed, more time must have passed. Einstein's explanation for this took an enormous leap of imagination, which became the basis of special relativity. Speed is a measure of units of distance per units of time. Therefore, the constancy of the speed of light must be due to an inconstancy in the flow of time. Objects observed to be traveling faster through space are moving more slowly through time. Clocks on the station and on the train are ticking at different rates, depending on the frame of reference from which they are observed. On the moving train, Bob sees his clock ticking away as normal, but to the observer Pat on the platform, the train's clock is moving very slowly. The passenger on the speeding train will not notice any slowing of time. The mechanisms by which time is measured, such as the swing of a pendulum, the vibration of a quartz crystal, or the behavior of an atom, are physical phenomena obeying universal laws. According to special relativity, laws remain unchanged within the reference frame, the moving train, or any other set of objects moving together. If you can't explain it to a 6-year-old, you don't understand it yourself. Albert Einstein. As an object's velocity approaches light speed, the object becomes increasingly squashed in the direction of travel when viewed by a stationary observer. This is not merely an illusion. In the observer's frame of reference, the object's shape really does change. Energy is mass. The impact of this dilation of time has far-reaching effects, which Einstein gradually pieced together into a single general theory of relativity in 1915. One early breakthrough was the discovery of E equals mc, which states that E is equal to mass multiplied by the square of the speed of light. C is a very large number, about 90 million billion, and so a small amount of mass contains a huge quantity of energy. This is evident in a nuclear explosion when mass is converted to free energy. Returning to the train thought experiment, the 2 observers now throw tennis balls at each other. The balls collide and bounce back to each person. If both observers were in the same reference frame, the described motion of the balls would occur because the balls had the same mass and were thrown with the same force. But in this experiment the balls are in different reference frames, one stationary, the other moving at close to the speed of light. Pat would see Bob's ball moving much more slowly than his own due to the time dilation, yet when they collide, both balls are knocked back to their owners. The only way this could work is if Bob's slow tennis ball is heavier, or contains more mass, than Pat's tennis ball. Therefore, according to special relativity, when matter moves, it becomes more massive. These mass increases can be measured on the everyday, human scale, but are negligible. However, they have a marked effect when objects are moving very quickly. For example, the protons accelerated by the Large Hadron Collider particle accelerator travel very close to the speed of light. Within 99.999% additional energy does very little to this speed, and instead boosts mass. At full power, the protons in the LHC are nearly 7,500 times more massive than they were when stationary. The twin paradox. A result known as the twin paradox is illustrated using a pair of newborn twins. One stays on Earth, while another is taken on a rocket on a journey to a star 4 light-years away. The rocket travels at an average velocity of 0.8 c, meaning that it returns from its 8 light-year journey on the 10th birthday of the twin who stayed on Earth. However, to the clock on the rocket, it is only the other twin's 6th birthday. The clock has been in a moving time frame, so has been ticking more slowly. Relativity insists that the twin on the rocket is also entitled to consider herself at rest, which seems to lead to a paradox. From her point of view, the twin on Earth had been the one moving. The paradox is resolved by the fact that only the twin in the rocket has undergone acceleration, with its consequent time dilation, both on the way out and to change direction and come back. The twin on Earth has remained in one frame of reference, while the twin on the rocket has been in two, one on the way out and another on the way back. Thus, the twin situations are not symmetrical, and the twin who stayed at home really is now 4 years older than her sister. The twin paradox has been a popular theme in science fiction. In the film The Planet of the Apes, astronauts return to Earth to find that thousands of years have elapsed, and the planet is now ruled by apes. In the film Interstellar, physics consultants were employed to ensure that the time elapsed for each character was correct according to relativity. Each ray of light moves in the coordinate system at rest, with a definite, constant velocity independent of whether this ray of light is emitted by a body at rest or a body in motion. Albert Einstein. Speed limit. With the relationship between speed and mass, relativity highlights another basic principle: the speed of light is the upper limit of motion through space. It is impossible for an object with mass, a nuclear particle, spaceship, planet, or star, to travel at the speed of light. As it approaches light speed, its mass becomes almost infinite, time slows nearly to a stop, and it would take an infinite amount of energy to push it to light speed. To generalize his theory, Einstein linked gravity to his ideas about energy and motion. Taking an object in space and removing all reference points, it is not possible to tell if it is moving. There is no test that can be done to prove that it is. Therefore, from the point of view of any object or reference frame, it stays still while the rest of the universe moves around it. Einstein's happiest thought. This is easiest to picture if everything is moving at a constant speed. According to Newton's first law of motion, an object maintains its motion unless a force acts to accelerate it. When Einstein included the effects of acceleration in his theory, it led to an insight that he called his happiest thought. It was not possible to differentiate why an object accelerated. It could be because of gravity, or it could be another force. The effect of both was the same and could be described by the way the rest of the universe moved around the reference frame. Einstein had described motion in terms of the links between mass, energy, and time. For a general theory, he needed to add space. It was not possible to understand the path of an object through space without considering its path through time. The result was that mass moves through spacetime, which has a four-dimensional geometry, as opposed to the usual 3 dimensions of the everyday concept of space. When an object moves through spacetime, the time dimension dilates, and the space dimensions contract. From the point of view of Pat back at the station, the speeding train's length is compressed, making it look very squashed and stubby. However, it is all normal to Bob. Anything he measures on board will have the same length as when the train was stationary. This is because his means of measurement, such as a ruler, has contracted along with space. The theory of relativity cannot but be regarded as a magnificent work of art. Ernest Rutherford, New Zealand physicist. From inside an elevator, a person cannot tell whether they are being accelerated upward by a force pushing the elevator from below or pulled downward by the gravity of a mass underneath the elevator. Either way, they feel a sense of weight as the floor pushes against them, and objects dropped from a height accelerate down to the floor. This is Einstein's equivalence principle, which he described as his happiest thought. A light beam shines into an elevator from an observer with a flashlight standing outside. The paths of the light beam are shown as they will be observed from inside the elevator. If the elevator is accelerating, the beam will curve downward. Light is similarly curved toward a source of gravity. Warping spacetime. In Einstein's universe, gravity is recast not as a force but rather the effect of warps in the geometry of spacetime caused by the presence of mass. A large mass, such as a planet, bends space, and so a smaller object, such as a meteor, moving in a straight line through space nearby, will curve toward the planet. The meteor has not changed course, it is still moving along the same line in space, it is just that the planet has bent that line into a curve. Warps in spacetime can be visualized as balls deforming a rubber sheet, making depressions or gravity wells. A large planet ball makes a well, and a smaller meteor ball will roll into the well. Depending on its trajectory, speed, and mass, the meteor might collide with the planet or roll back up the other side of the well and escape. If the trajectory is just right, the meteor will circle around the planet in an orbit. The warps created by matter also bend time. Two distant objects, for this explanation, a red star and a blue star, are not moving in relation to one another. They are in different points of space, but at the same point in time, the same now. However, if the red star moves directly away from the blue, its passage through time slows compared to the blue stars. That means the red star shares a now with the blue star in the past. If the red star travels directly toward the blue one, its now is angled toward the blue star's future. Consequently, events that are observed simultaneously from one reference frame may appear to occur at different times in another. Relativity solved the puzzle of perturbations in the orbit of the planet Mercury that could not be explained by Newtonian physics, which had first been noticed in 1859. Proof of relativity. Einstein's physics were initially met with bafflement from most of the scientific community. However, in 1919, the English astronomer Arthur Eddington demonstrated that this new way of describing the universe was indeed accurate. He traveled to the Atlantic island of Principe to observe a full solar eclipse and specifically to look at the background of stars near to the Sun. Light from stars travels to Earth along the most direct route, known as the geodesic. In Euclidean geometry, that is a straight line, but in the geometry of spacetime, a geodesic can be curved. So, starlight shining very close to the edge of the Sun passes into the warp created by the star's mass and follows a bending path. Eddington photographed the stars revealed by the absences of the solar glare. These images showed that the apparent position of the stars had indeed been shifted due to the warping of space, an effect now known as gravitational lensing. Einstein was proved right. Einstein's general theory of relativity allows astronomers to make sense of what they observe, everywhere from the very edge of the visible universe to the event horizon of a black hole. Today, the time dilations of relativity are taken into account in GPS technology, while the wave-like contractions of space predicted by relativity have recently been discovered in the LIGO experiment. Other ideas from relativity are also being used in the search for possible answers to the mystery of dark energy. Everything must be made as simple as possible. But not simpler. Albert Einstein. Mass creates a gravity well that causes an effect called gravitational lensing, first observed in 1919 by Arthur Eddington. The observed position of a star is changed by the effect of the Sun's gravity, which causes light from the star to travel past the Sun along a curved path. Time is an illusion. Albert Einstein. Albert Einstein. Einstein was born in Germany but spent his formative years in Switzerland. He was an average student, and then struggled to find teaching work, ending up at the patent office in Bern. After the success of his 1905 papers, Einstein took university posts in Bern, Zurich, and then in Berlin, where he presented his general theory in 1915. With the rise of Nazism in 1933, Einstein moved to the United States, where he settled at Princeton University. There he spent the rest of his days trying to link relativity with quantum mechanics. He failed to do so, and no one else has succeeded yet either. A leading pacifist voice for many years, in 1939 Einstein was instrumental in alerting allies to the dangers that Germany might build a nuclear weapon. He declined to be involved in the Manhattan Project that built the first atomic bombs. An avid violinist, Einstein stated that he often thought in music. Key work: 1915 Relativity, the Special and the General Theory. See also, Gravitational Theory Curves in Spacetime, the Birth of the Universe, Dark Energy, Gravitational Waves. In context. Key astronomer: Carl Schwarzschild. Before 1799 Pierre-Simon Laplace develops a theory about black holes, which he calls corps obscurs, or dark bodies. 1915 Albert Einstein's general theory of relativity shows that the force of gravity is caused by a warping of space and time. After 1931 Subramanian Chandrasekhar calculates the mass of stellar cores that become neutron stars and black holes. 1979 Stephen Hawking proposes that black holes do actually emit radiation as a result of quantum fluctuations. 1998 Andrea Ghez shows that a supermassive black hole sits at the center of the Milky Way. In 1916, German mathematician Carl Schwarzschild managed something that even Albert Einstein had failed to do. He provided a solution to the field equations of general relativity that could yield precise answers. The Einstein field equations are a complex set of formulae that link space and time with the action of gravity. Schwarzschild's achievement, known as the Schwarzschild solution, was to solve the equations to show exactly how spacetime curved in the presence of mass. This solution showed how the gravity of objects like the Sun and Earth was warping spacetime in accordance with the theories of relativity. A generation later, Schwarzschild's mathematics were used to throw light on the darkest of all objects, the black hole. No escape. In the early days of relativity, black holes were purely theoretical objects, although they had been predicted a century before. The French astronomer Pierre-Simon Laplace had theorized corps obscurs, objects so dense that the velocity required to escape their gravity exceeded the speed of light. The modern definition of black holes is similar: objects in space with such enormous gravity nothing can escape them, not even light. Event horizon. The Schwarzschild solution can be used to calculate the size of a black hole for a given mass. To create a black hole, mass must be compressed into a volume with a smaller radius than that predicted by the Schwarzschild solution. An object so dense that its radius is smaller than the Schwarzschild radius for its mass will warp spacetime to such an extent that its gravitational pull will be impossible to resist. It will create a black hole. Any mass or light that comes closer than the Schwarzschild radius is doomed to be pulled into the black hole. The points in space that surround a black hole at a distance of the Schwarzschild radius form its event horizon, so called because it is impossible to observe the events that take place beyond it. Nothing comes out of a black hole, no mass, no light, and no information about what is inside. The Schwarzschild solution allows astronomers to estimate the masses of actual black holes, although it is not possible to be exact because black holes rotate and carry an electric charge, and these factors are not accounted for by the mathematics. If the Sun became a black hole, its event horizon would be 2 miles from the center. A black hole with Earth's mass would have a in radius. However, it is not possible to make black holes from bodies this small. It is thought that black holes form from collapsed stars that are at least 3 solar masses. It is theorized that beyond the event horizon, at the center of the black hole, lies a singularity, a point of infinite gravity and infinite density. However, it is impossible to obtain information from beyond an event horizon. In this diagram, one of the 3 dimensions of space has been removed to aid visualization. Carl Schwarzschild. Carl Schwarzschild's prodigious mathematical abilities were obvious from an early age. By the age of 16, he had published his first scientific paper concerning the mechanics of binary orbits, and by 28, he was a professor at the University of Göttingen in Lower Saxony. Schwarzschild made contributions to the most significant sciences of the age: radioactivity, atomic theory, and spectroscopy. In 1914, he joined up to fight in World War I, but still found time for mathematics. In late 1915, he sent Albert Einstein some early calculations, saying, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." The following year, Schwarzschild presented the full solution that bears his name. He developed an autoimmune disease while serving on the Russian front and died in May 1916. Key work: 1916 on the gravitational field of a mass point after Einstein's theory. See also, gravitational disturbances, the theory of relativity, the life cycles of stars. Hawking radiation, the heart of the Milky Way. In context. Key astronomer Vesto Slipher. Before 1842, Austrian physicist Christian Doppler proposes the Doppler effect, a change in the perceived frequency of waves coming from an object moving relative to the viewer. 1868, William Huggins determines the velocity of a star moving away from Earth using the Doppler effect. After 1929, Edwin Hubble finds a link between the recessional velocities of spiral galaxies and their distances. 1998, Saul Perlmutter and his colleagues discover that the expansion of the universe has been accelerating for the last 5 billion years. In the 1780s and 1790s, British astronomer William Herschel catalogued large numbers of nebulae and speculated that some of these might be comparable in size and nature to the Milky Way. In his conjectures, Herschel was following an earlier suggestion by German philosopher Immanuel Kant that nebulae might be large disks of stars, island universes, independent of the Milky Way and separated from it by vast distances. In the 19th century, using improved telescopes, British astronomer Lord Rosse discovered that some nebulae had arms arranged in a spiral, while his compatriot William Huggins found that many nebulae consisted of a mass of stars. However, aside from the fact that they might contain stars, nebulae were still little understood by the turn of the 20th century, when a young scientist from Indiana named Vesto Slipher began to study them. It seems to me that with this discovery, the great question, if the spirals belong to the system of the Milky Way or not, is answered with great certainty: they do not. Ejner Hertzsprung in a letter to Vesto Slipher. The Lowell Observatory. From 1901, Slipher worked at the Lowell Observatory in Flagstaff, Arizona. The observatory had been founded by American astronomer Percival Lowell in 1894. Lowell had selected the site because its high altitude, at over 6,900 feet, with few clouds, and its distance from city lights, meant it guaranteed good visibility almost every night. Lowell's venture marked the first time an observatory had been built deliberately in a remote, high place for optimal observations. Lowell initially hired him for a short-term position, but Slipher would remain for his entire career. Lowell and Slipher worked well together, with the unassuming new recruit content to leave the limelight to his flamboyant employer. Slipher was a talented mathematician and had practical mechanical skills, which he put to use installing new spectrographic equipment. He set to work developing improved techniques in spectrography, the separation of light coming from celestial objects into its constituent wavelengths, and the measurement and analysis of those wavelengths. Slipher used the 24 inches Alvan Clark telescope at the Lowell Observatory to observe the spiral nebulae. Today, people can use the original telescope at the observatory's visitor center. Studying nebulae. Slipher's initial work and research were directed at the planets, but from 1912, at Lowell's request, he began to study the mysterious spiral nebulae. Lowell had a theory that they were spirals of gas that were coalescing into new solar systems. He asked Slipher to record the spectra of the light from the outer edges of the nebulae, to determine if their chemical makeup resembled that of the solar system's gas giant planets. Making small adjustments to its mechanism, Slipher managed to increase the sensitivity of Lowell's spectrograph, a complex 450-pound instrument attached to the eyepiece of the observatory's 24-inch refractor telescope. During the fall and winter of 1912, he obtained a series of spectrograms from the largest of the spiral nebulae, which was located in the constellation of Andromeda and known at the time as the Andromeda Nebula. The pattern of spectral lines in the nebula's spectrum indicated a blue shift. They were unexpectedly displaced toward the short wavelength high-frequency blue end of the spectrum by what is known as a Doppler shift. That could only mean that the light waves coming from the Andromeda Nebula were being shortened, or compressed, and their frequency raised, because the nebula was rushing toward Earth at a considerable speed. Slipher's calculations revealed that the nebula was approaching at 200 miles per second. Doppler shifts had been measured for astronomical bodies before, but shifts of this size were unprecedented. Slipher asserted that we have at the present no other interpretation for it. We may conclude that the Andromeda Nebula is approaching the solar system. The spectra of galaxies moving toward Earth exhibit blue shifts, and those receding from Earth exhibit red shifts because the light waves are squashed or stretched when viewed from Earth. These are called Doppler shifts after the Austrian physicist Christian Doppler, who first explained such phenomena. Discovering Doppler shifts. Over the next few years, Slipher studied 14 more spiral nebulae and found that nearly all were traveling at incredible speeds relative to Earth. Most remarkably, whereas some were moving toward Earth, most were showing redshifted spectra, where the wavelengths had stretched, meaning they were moving away from Earth. The nebula known as M104, for example, was flying away at an astonishing speed of nearly 600 miles per second. Another called M77, or NGC 1068, was receding at 680 miles per second. Altogether, out of the 15 galaxies observed, 11 were significantly redshifted. In 1914, Slipher presented his results to the American Astronomical Society and received a standing ovation. By the time Slipher had presented his next paper on spiral nebulae in 1917, the ratio of redshifted to blue-shifted nebulae had risen to 21:4. In this paper, Slipher noted that the average velocity at which they were approaching or receding, scientifically known as radial velocity, was 450 miles per second. This was much faster than any star had ever been measured moving relative to Earth. Slipher found it almost inconceivable that the spiral nebulae could be passing through the Milky Way at such speeds, and he began to suspect that they were not moving through the Milky Way at all, stating, "It has for a long time been suggested that the spiral nebulae are stellar systems seen at great distances. This theory, it seems to me, gains favor in the present observations." Slipher was echoing Kant's suggestion that some nebulae, in particular the spiral ones, could be separate galaxies from the Milky Way. In 1920, partly prompted by Slipher's findings, a formal debate took place in Washington, D.C., to discuss whether the spiral nebulae were separate galaxies outside the Milky Way. Now referred to as the Great Debate, two eminent American astronomers advocated opposing positions, Harlow Shapley that the spiral nebulae were part of the Milky Way, and Heber D. Curtis that they were far beyond it. Neither astronomer changed his position as a result of the debate, but many perceptive figures were concluding by this time that the spirals had to be outside the Milky Way. The galaxy NGC 4565, which Slipher established to be receding at 700 miles s, is also known as the Needle Galaxy because of its thin shape when viewed from Earth. Slipher's legacy. Despite an enthusiastic response from many in the astronomical community, some still questioned Slipher's findings. For more than a decade, until others began to believe Slipher's ideas and understand the implications arising from them, he was virtually the only person investigating the Doppler shifts of spiral nebulae. In 1924, a new paper by American astronomer Edwin Hubble put a decisive end to the debate about the nature of spiral nebulae. Hubble had observed a class of stars called Cepheid variables in some nebulae, including the Andromeda Nebula. As a result of his observations, Hubble was able to announce that the Andromeda Nebula and others like it were far too distant to be part of the Milky Way and so must be galaxies outside it. Slipher's suspicions dating back to 1917 had been proved right. By the time of Hubble's paper, Slipher had measured the radial velocities of 39 spiral nebulae, the majority of which showed high velocities of recession, as much as 775 miles per second. Hubble used Slipher's measurements of redshifts in galaxies that he had proved were outside the Milky Way to find a relationship between galaxy redshifts and distances. By the late 1920s, Hubble had used this result to confirm that the universe is expanding. Thus, Slipher's work in the years 1912-25 played a crucial role in what today is often considered the greatest astronomical discovery of the 20th century, paving the way for further investigations into the motions of galaxies and cosmological theories based on an expanding universe. As for the Andromeda Galaxy, it is expected to collide with the Milky Way in about 4 billion years, and together the two are likely to form a new elliptical galaxy. In the great majority of cases the nebula is receding, the largest velocities are positive. The striking preponderance of indicates a general fleeing from us or the Milky Way. Vesto Slipher. Some 4 billion years into the future, the night sky will look like this, as the Andromeda Galaxy collides with the Milky Way. Vesto Slipher. Vesto Slipher was born on a farm in Mulberry, Indiana, in 1875. Soon after graduation, he started working at the Lowell Observatory in Arizona, where he would remain for more than half a century. Most of Slipher's major discoveries occurred in the earlier part of his career. He began by investigating the rotational periods of planets, finding evidence, for example, that Venus's rotation is very slow. Between 1912 and 1914, he made his most significant discovery, that some spiral nebulae are moving at high speed. In 1914, Slipher discovered the rotation of spiral galaxies, measuring spin rates of hundreds of miles per second. He also demonstrated that gas and dust exist in interstellar space. Slipher was director of the Lowell Observatory from 1926 to 1952. During this time, he supervised a search for trans-Neptunian planets, which led in 1930 to Clyde Tombaugh's discovery of Pluto. Key work: 1915 Spectrographic observations of nebulae. See also, the Milky Way, examining nebulae, properties of nebulae, measuring the universe, the shape of the Milky Way, the birth of the universe beyond the Milky Way. In context. Key astronomer: Cecilia Payne-Gaposchkin. Before 1850s Gustav Kirchhoff shows that dark lines in the sun's spectrum are due to light absorption by elements. 1901 Annie Jump Cannon classifies stars by the strength of the dark lines in their spectra. 1920 Indian physicist Meghnad Saha demonstrates how temperature, pressure, and ionization are linked in a star. After 1928, 29 Albrecht Unsold and William McRae independently find that hydrogen is 1,000,000 times more abundant in the sun's atmosphere than any other element. 1933 Danish astrophysicist Bengt Stromgren shows that stars are mainly hydrogen all the way through, not just in their atmospheres. In 1923, the consensus among astronomers was that the Sun and other stars had a similar chemical composition to Earth. This belief was based on the analysis of dark lines in star spectra, which are caused by the absorption of light by chemical elements in star atmospheres. The spectra contain strong lines for elements that are common on Earth, such as oxygen and hydrogen, and metals such as magnesium, sodium, and iron, and therefore it was assumed that Earth and stars were made of the same chemical elements, in more or less the same proportions. This established view would be overturned with the arrival that year of British graduate student Cecilia Payne at the Harvard College Observatory in Massachusetts. The reward of the old scientist is the sense of having seen a vague sketch grow into a masterly landscape. Cecilia Payne-Gaposchkin. Star spectra. Payne set to work analyzing the HCO's photographic collection of star spectra. She wanted to clarify the relationship between star spectra and temperatures. Also, because the pattern of absorption lines seemed to vary between the spectra of different classes of star, she wanted to see what differences in chemical composition might exist between these classes. Since 1901, astronomers at the HCO had classified stars into a sequence of 7 main spectral types, and believed that the sequence was related to the star's surface temperatures. In her doctoral thesis, however, Payne applied an equation formulated by Indian physicist Meghnad Saha in 1920. The equation related a star's spectrum to the ionization of chemical elements in its atmosphere and the ionization of its surface temperature. Payne demonstrated a link between the spectral classes of stars and their surface temperatures. She also showed that the variation in absorption lines between star spectra was due to varying amounts of ionization at different temperatures, and not to varying abundances of chemical elements. Payne knew that the intensity of absorption lines in star spectra could give only crude estimates of chemical elements, so other factors needed to be taken into account, such as the ionization states of the atoms of different elements. Using her knowledge of atomic physics, she determined the abundances of 18 elements found in the spectra of many different stars. She found that helium and hydrogen were vastly more abundant than on Earth, making up nearly all the matter in stars. Hydrogen and helium together make up 98% of all of the matter throughout the galaxy that is made of atoms. Astronomers' reaction. In 1925, Payne's thesis was sent to the astronomer Henry Russell for review. Russell declared that Payne's results were clearly impossible, and pressured her to include a statement saying that the levels of hydrogen and helium she had found were almost certainly not real. 4 years later, however, Russell conceded that Payne was right. Payne's discoveries were revolutionary. First, she established that most stars are chemically similar. Second, she demonstrated how to determine the temperature of any star from its spectrum. Third, she showed that hydrogen and helium are dominant elements in the universe, a key step toward the Big Bang theory. If you are sure of your facts, you should defend your position. Cecilia Payne-Gaposchkin. Cecilia Payne-Gaposchkin. Cecilia Payne was born in Wendover, England, in 1900. At age 19, she won a scholarship to Newnham College, Cambridge, where she studied botany, physics, and chemistry. After attending a lecture by Arthur Eddington, she switched to astronomy. In 1923, she left for the U.S. to join a new graduate course in astronomy at Harvard College Observatory. Within 2 years, she had produced her revolutionary doctoral thesis, Stellar Atmospheres. Much of her research focused on variable stars and novae. This work helped explain the Milky Way's structure and the paths of stellar evolution. In 1931, she became a U.S. citizen and in 1934 married Russian astronomer Sergei Gaposchkin. In 1956, she was made professor of astronomy at Harvard University, the first female professor at Harvard. She died in 1979. Key works: 1925 Stellar Atmospheres and 1938 Variable Stars. 1957 Galactic Novae. See also, the Sun's spectrum, the characteristics of stars, nuclear fusion within stars, energy generation. In context. Key astronomer Bertil Lindblad. Before 1904 Jacobus C. Kapteyn shows how stars can be divided into two streams moving in opposite directions. 1917 Vesto Slipher shows that spiral nebulae are moving faster than any star. 1920 Harlow Shapley predicts that the center of the galaxy is in Sagittarius, estimating it at 50,000 light-years away. After 1927 Jan Oort confirms that the galaxy is rotating and proposes that a large mass of stars forms a bulge at its core. 1929 Edwin Hubble shows that other galaxies lie far beyond the Milky Way. 1979 Vera Rubin uses galactic rotation to show that galaxies contain invisible dark matter. In the 1920s, there were two opposing views of the universe. Some astronomers thought the Milky Way was itself the entire universe. Others argued that the spiral nebulae observed were not cloudy masses on the edge of the Milky Way, but galaxies in their own right a vast distance away. In 1926, a Swedish astronomer named Bertil Lindblad considered the likely shape of the Milky Way, concluding that it took the form of a rotating spiral. Lindblad was building on the work of two other astronomers. The first was the American Harlow Shapley, who believed that the Milky Way made up the whole universe. Shapley suggested that the edge of the galaxy could be plotted using the many globular clusters of stars that had been observed, and that the center lay in Sagittarius. The second was the Dutchman Jacobus C. Kapteyn, who had described a phenomenon he called star streaming. Stars did not move in random directions, Kapteyn said, but appeared to move in groups, going either one way or in the opposite direction. Lindblad himself was a leading expert in measuring the absolute magnitude of stars from their spectra, and was able to calculate their distances from Earth. He combined this data with his observations of the motion of globular clusters and made an interesting discovery. The Solar System is orbiting the center of the Milky Way at a speed of 140 miles s, stars closer to the center orbit at a faster speed. Spinning in subsystems. Lindblad saw that stars move in subsystems, and each subsystem moves at a different speed. From this, he deduced that Kapteyn's star streaming was in fact evidence of the galaxy rotating, which meant that the Milky Way's stars were all moving in the same direction around a central point. Stars that streamed ahead of the Solar System were nearer to the center, and stars that were farther from it appeared to stream in the opposite way because they were lagging behind. As Shapley had predicted, Lindblad placed the galactic center in Sagittarius. He supposed that subsystems farther from the galactic center orbited more slowly than the ones closer in. This was confirmed in 1927 by the observations of Jan Oort, one of Kapteyn's students. The Milky Way was revealed to be a swirling disk that spun, albeit very slowly, taking 225 million years to complete one orbit. Although Lindblad had offered no evidence of bodies lying outside the Milky Way, his disc-shaped galactic model with a bulging core gave credence to the idea that similar-looking objects were also galaxies. However, Oort's observations would also reveal a new puzzle. The galaxy appeared to be rotating faster than could be accounted for by the mass of its visible matter. Here was the first hint of a mystery that endures today: dark matter. Bertil Lindblad. Bertil Lindblad grew up in Örebro, Sweden. He did his undergraduate degree at Uppsala University, north of Stockholm, and became an assistant at the observatory there. It was while working at Uppsala that Lindblad made his observations of the motion of globular clusters that led to his theory of galactic rotation, which was published in 1926. The following year, still barely into his 30s, Lindblad was offered the directorship of the Stockholm Observatory and became the chief astronomer for the Royal Swedish Academy of Sciences. He held that position until his death, overseeing many improvements. In later years, he was a leading organizer for the European Southern Observatory, which has been located in the high desert of Chile since 1962, and president of the International Astronomical Union. Key works: 1925 Star Streaming and the Structure of the Stellar System. 1930 The Velocity Ellipsoid, Galactic Rotation, and the Dimensions of the Stellar System. See also, Spiral Galaxies Beyond the Milky Way, the Oort Cloud, Dark Matter. In context. Key astronomer: Arthur Eddington. Before 1890s Briton Lord Kelvin and German Hermann von Helmholtz suggest that the Sun gets its energy by shrinking. 1896 physicist Henri Becquerel discovers radioactivity. 1906 Karl Schwarzschild shows that energy can travel through a star by radiation. After 1931 Robert Atkinson sets out the process by which protons can combine to release energy and build new elements. 1938 German physicist Carl von Weizsäcker discovers that protons can combine into helium in stars by the carbon-nitrogen-oxygen cycle. 1939 Hans Bethe details how the proton-proton chain and CNO cycle processes work. In the 1920s, British astronomer Arthur Eddington was the first person to explain the processes at work inside stars. He championed the idea that their source of energy is nuclear fusion. A stable sun. When looking at the Sun from Earth, what can actually be seen is the gaseous surface layer in the top 300 miles or so, which has a temperature of about 9,900 degrees Fahrenheit. The Sun appears to be in equilibrium, meaning that, over the centuries in which astronomers have observed it, it has always appeared to be the same size and show the same luminosity. Eddington realized that the gravitational force pulling inward would be balanced not only by the gas's tendency to expand outward but also by the pressure produced by the radiation pouring out of the star. Eddington was able to show convincingly that all stars are giant balls of hot gas. He calculated how luminous stars of different masses would appear if the gas in their centers, where the temperature and density are very high, followed the same physical laws as cooler, less dense gas. The answers he obtained were a good match for observations of both giant and dwarf stars. Since all gases obey the same laws, assuming that the Sun is not only gaseous at the surface but throughout allows the calculation of the temperature and pressure at the center. Gas laws and relativity. The physical laws governing the relationships between the pressure, volume, and temperature of a gas were well understood. Since they all have widely spaced molecules, gases behave in similar ways. For instance, Boyle's law states that, at a constant temperature, the product of the pressure and volume of a given mass of gas is constant. Eddington used these laws to calculate that the temperature at the center of the Sun is about 29 million degrees Fahrenheit, with a density 150 times that of water. To understand what was going on in the Sun's center, Eddington now needed Einstein's equation E equals mc. This equation states that energy is equal to mass multiplied by the square of the velocity of light. It was the key to unlocking the mystery of the source of the Sun's energy, as it showed how mass could be turned into energy. The conditions at the solar center were sufficiently hot and dense to allow nuclear reactions to take place and mass to be destroyed, thus producing the energy that Einstein's equation predicted. At first, physicists suggested that individual electrons or hydrogen atoms might be the mass that went into Einstein's equation. In 1931, Welsh astrophysicist Robert Atkinson showed that a process in which 4 hydrogen atoms were fused into one slightly less massive helium atom fit the data from the Sun. This process is very slow and produces energy to fuel the Sun for billions of years. Here also was evidence of the transmutation of the elements, showing how the composition of the universe changes with time. It is sound judgment to hope that, in the not-too-distant future, we shall be competent to understand so simple a thing as a star. Arthur Eddington. Arthur Eddington. Arthur Eddington was born into a Quaker family, and was educated in mathematics and physics at the universities of Manchester and Cambridge. In 1905, he joined the Royal Observatory, Greenwich, but a few years later he returned to Trinity College, Cambridge, becoming Plumian Professor in 1913 and Director of the Cambridge University Observatory in 1914. He lived there for the rest of his life. In 1919, Eddington sailed to Principe Island, West Africa, to observe a total solar eclipse and test Einstein's prediction about the bending of starlight by the Sun. He was a brilliant astronomer and mathematician, and able to communicate the most difficult physical idea in a simple and elegant language. This made his books extremely popular, especially his explanations of relativity and quantum mechanics. Key works. 1923 The Mathematical Theory of Relativity. 1926 The Internal Constitution of the Stars. See also, The Theory of Relativity, Stellar Composition, Energy Generation, Nucleosynthesis. In context. Key astronomer. Georges Lemaitre. Before 1915 Albert Einstein publishes his general theory of relativity, which includes equations that define various possible universes. 1922 Alexander Friedmann finds solutions to Einstein's equations, indicating that the universe could be expanding, contracting, or static. After 1929 Edwin Hubble observes that distant galaxies are moving away from Earth at a rate proportional to their distance. 1949 Fred Hoyle coins the term Big Bang for Lemaitre's theory. The idea that the universe originated from a tiny object in the form of an egg appears in the Rigveda, a collection of Hindu hymns from the 12th century BCE. However, there were few scientific clues to the universe's true origins until Albert Einstein provided a new way of conceiving time and space with his general theory of relativity in 1915. Einstein's insight led many to revisit the idea that the universe started small, among them the Belgian priest Georges Lemaitre, whose 1931 proposal would carry echoes of the Rigveda. In the 17th century, Johannes Kepler, observing that the night sky is dark, argued that the universe cannot be infinite in both time and space, as otherwise the stars shining from every direction would make the whole sky bright. His argument was restated in 1823 by German astronomer Wilhelm Olbers and became known as Olbers' paradox. Despite this problem, Isaac Newton stated that the universe was static and infinite in time and space, with its matter distributed more or less uniformly over a large scale. At the end of the 19th century, this was still the prevailing view, and one that Einstein himself initially held. Olber's paradox is the argument that, if the universe is infinite, not expanding, has always existed, and everywhere contains roughly the same density of stars, then any sight line from Earth must end at the surface of a star. The night sky should be uniformly bright, but this contradicts the observed darkness of the night. An unchanging universe. Einstein's general theory of relativity explains how gravity works at the largest scales. He realized that it could be used to test whether the Newtonian model of the universe could exist long-term without becoming unstable, and to explore which other types of universe might be feasible. The exact relationship between mass, space, and time was explained in a series of 10 complex equations. These were called Einstein's field equations. Einstein found an initial solution to his equations that suggested the universe is contracting. Since he could not believe this, he introduced F(x), an expansion-inducing factor called the cosmological constant, to balance the inward pull of gravity. This allowed for a static universe. In 1922, Russian mathematician Alexander Friedmann attempted to find solutions to Einstein's field equations. Starting with the assumption that the universe is homogeneous and spread out evenly in every direction, he found several solutions. These allowed for models in which the universe could be expanding, contracting, or static. Friedmann was probably the first person to use the expression expanding universe. Einstein first called his work suspicious, but 6 months later acknowledged that his results were correct. However, this was Friedmann's final contribution as he died 2 years later. In 1924, Edwin Hubble showed that many nebulae were galaxies outside the Milky Way. The universe had suddenly become a lot bigger. The expanding universe. Later in the 1920s, Lemaitre entered the debate about the large-scale organization of the universe. He had worked at institutions in the United States, becoming aware of Vesto Slipher's work on receding galaxies and Hubble's measurements of galaxy distances. A competent mathematician, he had also studied Einstein's field equations and found a possible solution to the equations that allowed for an expanding universe. Putting these various threads together, in 1927, Lemaitre published a paper that proposed that the whole universe is expanding and carrying galaxies away from each other and from Earth. He also predicted that galaxies that are more distant from us would be found to be receding at a faster rate than closer ones. Lemaitre's paper was published in an obscure Belgian journal, and as a result, his hypothesis failed to attract much attention at the time. He did, however, communicate his findings to Einstein, telling him of the solution he had found to the field equations allowing for a universe that expands. Einstein introduced Lemaitre to Friedmann's work, but remained ambivalent about Lemaitre's idea. Famously, Einstein is said to have said, "Your calculations are correct, but your grasp of physics is abominable." However, the British astronomer Arthur Eddington later published a long commentary on Lemaitre's 1927 paper, describing it as a brilliant solution. In 1929, Hubble released findings showing that there was indeed a relationship between the remoteness of a galaxy and how fast it was receding, confirming for many astronomers that the universe was expanding, and that Lemaitre's paper had been correct. For many years the credit for the discovery of the expansion of the universe was given to Hubble, but today most agree it should be shared with Lemaitre and possibly also with Alexander Friedmann. The primeval atom. Lemaitre reasoned that, if the universe is expanding and the clock is run backward, then far back in time, all the matter in the universe must have been much closer. In 1931, he suggested that the universe was initially a single, extremely dense particle containing all its matter and energy, primeval atom as he called it, about 30 times the size of the Sun. This disintegrated in an explosion, giving rise to space and time on a day without yesterday. Lemaitre described the beginning of the universe as a burst of fireworks, comparing galaxies to the burning embers spreading out from the center of the blast. The proposal initially met with skepticism. Einstein found it suspect but was not altogether dismissive. In January 1933, however, Lemaitre and Einstein traveled together to California for a series of seminars. By this time, Einstein was in full agreement with Lemaitre's theory, calling it the most beautiful and satisfactory explanation of creation to which I have ever listened. Lemaitre's model also provided a solution to the long-standing problem of Olbers' paradox. In his model, the universe has a finite age, and because the speed of light is also finite, that means that only a finite number of stars can be observed within the given volume of space visible from Earth. The density of stars within this volume is low enough that any line of sight from Earth is unlikely to reach a star. The radius of space began at 0, and the first stages of the expansion consisted of a rapid expansion determined by the mass of the initial atom. Georges Lemaitre. Refining the idea. Compressed into a tiny point, the universe would be extremely hot. During the 1940s, Russian-American physicist George Gamow and colleagues worked out details of what might have happened during the exceedingly hot first few moments of a Lemaitre-style universe. The work showed that a hot early universe, evolving into what is observed today, was theoretically feasible. In a 1949 radio interview, the British astronomer Fred Hoyle coined the term Big Bang for the model of the universe Lemaitre and Gamow had been developing. Lemaitre's hypothesis now had a name. Lemaitre's idea about the original size of the universe is now considered incorrect. Today, cosmologists believe it started from an infinitesimally small point of infinite density called a singularity. A parallel exists between the Big Bang and the Christian notion of creation from nothing. George Smoot. Lemaitre's model of a universe expanding from an initial extremely dense concentration of mass and energy is today called the Big Bang model of the universe. Although Lemaitre described the initial stages of the process as an explosion, the prevailing view today is that expansion is a fundamental quality of space itself, and this carries galaxies away from each other, rather than being projected by the initial explosion into a pre-existing void. Georges Lemaitre. Georges Lemaitre was born in 1894 in Charleroi, Belgium. Following distinguished service in World War I, in 1920 he was awarded a doctoral degree in engineering. He subsequently entered a seminary where, in his leisure time, he studied mathematics and science. After his ordination in 1923, Lemaitre studied mathematics and solar physics at Cambridge University, studying under Arthur Eddington. In 1927, he was appointed professor of astrophysics at the University of Leuven, Belgium, and published his first major paper on the expanding universe. In 1931, Lemaitre put forward his theory of the primeval atom in a report in the journal Nature, and his fame soon spread. He died in 1966, shortly after learning of the discovery of cosmic microwave background radiation, which provided evidence for the Big Bang. Key works. 1931 The beginning of the world from the point of view of quantum theory. 1946 The primeval atom hypothesis. See also, gravitational theory, the theory of relativity, spiral galaxies beyond the Milky Way, the primeval atom. In context. Key astronomer Edwin Hubble. Before 1907 Henrietta Swan Leavitt shows the link between period and luminosity of Cepheid stars. 1917 Vesto Slipher publishes a table of 25 galactic redshifts. 1924 Hubble shows that the Andromeda Galaxy lies well outside the Milky Way. 1927 Georges Lemaitre proposes that the universe may be expanding. After 1998 The Supernova Cosmology Project and High-Z Supernova Search prove that cosmos expansion is accelerating. 2001 Hubble Space Project measures the Hubble constant to within 10%. 2015 The Planck Space Observatory puts the age of the universe at 13.799 billion years. In the early 1920s, American astronomer Edwin Hubble provided proof of the true size of the universe. Working at the Mount Wilson Observatory near Pasadena, California, Hubble used the newly constructed 100-inch Hooker telescope, at that time the largest in the world, to settle the greatest argument then raging in astronomy. His observations would lead to the startling revelation that the universe is not only far, far larger than previously thought, but is also expanding. Settling the Great Debate. At the time, the question of whether spiral nebulae were galaxies beyond the Milky Way or a special kind of nebula was the subject of a great debate. In 1920, a meeting was held at the Smithsonian Museum in Washington, D.C., in an attempt to settle the question. Speaking for the small universe was Princeton astronomer Harlow Shapley, who contended that the Milky Way comprised the entire universe. Shapley cited as evidence reports that the spiral nebulae were rotating, reasoning that this must make them relatively small because otherwise the outer regions would be spinning at speeds faster than the speed of light. Opposed to Shapley was Heber D. Curtis, who supported the idea that each nebula was far beyond the Milky Way. Curtis cited as evidence the discovery by Vesto Slipher that light from most spiral nebula galaxies was shifted to the red part of the electromagnetic spectrum, indicating that they were moving away from Earth at enormous speeds far too high for them to be contained within the Milky Way. Hubble set out to see whether there was a relationship between the distances of spiral nebulae and their velocity. His strategy was to search for Cepheid variable stars whose luminosity changes predictably, within nebulae and to measure their distances from Earth. This provided Hubble with his first big discovery in the winter of 1923. Beginning with photographic plates of the closest and clearest nebulae, Hubble spotted a Cepheid variable on one of the first plates he reviewed. The distances he calculated for even relatively nearby nebulae were so vast that it effectively killed the great debate immediately. NGC 6822 was 700,000 light-years away, while M33 and M31 were 850,000 light-years away. It was instantly clear that the universe extended beyond the Milky Way. Just as Curtis had maintained, the spiral nebulae were island universes, or extragalactic nebulae as Hubble termed them. Over time, the term spiral nebulae fell into disuse and they are now simply called galaxies. Observations indicate that the universe is expanding at an ever-increasing rate. It will expand forever, getting emptier and darker. Stephen Hawking. Hubble is seen here looking through the lens of the Hooker telescope at Mount Wilson. It was here that he measured galaxy distances and a value for the expansion of the universe. In the realm of the nebulae, Hubble pressed ahead with his program of measuring the distances to galaxies beyond the Milky Way. Farther out, however, it became impossible to pick out individual Cepheid variables in such faint and fuzzy distant galaxies. He was compelled to fall back on indirect methods, such as the so-called standard ruler assumption. Reasoning that all galaxies of a similar type are the same size allowed him to estimate the distance to a galaxy by measuring its apparent size and comparing it to the expected true size. Thanks to Slipher's measurements, Hubble already knew that light from most spiral nebulae was redshifted. In addition, the fainter spirals had higher values of redshift, showing that they were moving faster through space. Hubble realized that, if there were indeed a relationship between a galaxy's distance from Earth and its recession velocity, these redshifts would serve as a cosmic yardstick, enabling the distances of the very farthest and faintest galaxies to be calculated, and a ballpark figure to be put on the size of the universe as a whole. Meanwhile, Milton Humason, the assistant astronomer at Mount Wilson, checked Slipher's redshifts and collected new spectra from distant galaxies. It was hard, punishing work, and he and Hubble spent many bitterly cold nights in the observer's cage at the top of the Tube Telescope on Wilson Mountain in California. Hubble's landmark paper, A Relationship Between Distance and Radial Velocity Among Extragalactic Nebulae, was published in a journal called Proceedings of the National Academy of Science in 1929. It contained a straight-line graph that plotted 46 galaxies from near to far against their redshifts. Although there was a considerable scatter, Hubble managed to fit a straight line through the majority. The graph shows that, with the exception of the nearest galaxies, Andromeda and Triangulum, which are encroaching on the Milky Way, all other galaxies are receding. What is more, the farther away they are, the faster their movement. Toward an interpretation. If, from Earth's perspective within the universe, all galaxies are seen flying away, then the potential explanations are that Earth lies at the center of the universe, or the universe itself originated from a single point and is expanding as a whole. Objectivity, a kind of foundational law in science, requires that there is no reason to assume that Earth occupies a unique position. Instead, the light from distant nebulae showed that the universe was not static. Many astronomers quickly reached the conclusion that this was due to the expansion of the universe, although Hubble never stated this explicitly. In reality, Vesto Slipher had indicated the trend in 1919, 4 years before Hubble made his observations, and Georges Lemaître had proposed the expansion of the universe from a primeval atom in 1927. However, Hubble's result provided a simple link between his redshift measured velocities and distance, and with it, the convincing proof that the scientific community needed. Hubble's law, stating that the redshift of galaxies is proportional to their distance from Earth, was accepted almost unanimously. Equipped with his five senses, man explores the universe around him and calls the adventure science. Edwin Hubble. Einstein's blunder. The revelation that the universe might be expanding made news all over the world, not least for the fact that it directly contradicted a theory of Albert Einstein's. Einstein saw that gravity could eventually cause the universe to collapse under its own weight, so he used a value he called the cosmological constant, a kind of negative pressure, to prevent this from occurring in the field equations of general relativity. He abandoned the idea in the wake of Hubble's discovery. Einstein and others assumed that the observed velocities were Doppler effects caused by the galaxy's speed of recession, but there were some dissenting voices. Swiss astronomer Fritz Zwicky suggested that the redshift might be due to tired light reaching Earth, caused by the interaction of photons with the intervening matter. Hubble himself found it hard to believe that the velocities indicated by the redshifts were actually real, and was happy to use them solely as distance indicators. In fact, the velocities of galaxies observed by Hubble are due to the expansion of spacetime itself. Here, the galaxies of the universe are imagined as dots stuck to an inflating balloon. As the balloon doubles in diameter, the distances between dots also double. The farther away a dot is from another dot, the farther, and so more quickly, it moves. C has moved 2 centimeters from A, but B has moved just 1 centimeter from A. K-factor. Hubble showed how fast spacetime is expanding by plotting a straight-line graph, which he grandly called the K-factor. The gradient is described mathematically by a value now known as the Hubble constant. This important number determines not only the size of the observable universe but also its age. The Hubble constant allowed astronomers to work backward and calculate the moment in time of the Big Bang itself, when the radius of the universe was 0. The initial calculation of h was 300 miles per second per megaparsec. This presented a problem, since it gave a figure of 2 billion years for the age of the universe, less than half the accepted age of Earth. The discrepancy was found to have been caused by systematic errors in Hubble's distance measurements. Many were out by a factor of 7 due to his method of taking the brightest star in any galaxy, or even the luminosity of the galaxy itself, and assuming it to be a Cepheid variable star. Luckily for Hubble, the inaccuracies were fairly consistent throughout the dataset, allowing him to plot the trend in spite of them. The ESA's Planck Observatory operated between 2009 and 2013. It produced data that helped to measure many cosmological parameters, including the Hubble constant. Hubble Key Project. Calculating the rate of expansion of the cosmos drove the decision to develop the Hubble Space Telescope from its inception in the 1970s to its 1990 launch. NASA made one of the telescope's key projects determining the Hubble constant to within 10%. As a result, the instrument spent years measuring Cepheid light curves. The final result, delivered in 2001, gave an age for the universe of 13.7 billion years. This figure was fine-tuned to 13.799 billion years by data from the Planck Space Observatory in 2015. The most dramatic revision to Hubble's law, however, came in 1998 when astronomers discovered that the universe's expansion is accelerating due to a mysterious and unknown agent known as dark energy, which has led to a renewal of interest in Einstein's so-called blunder, the cosmological constant. Edwin Hubble. Born in 1889 in Missouri, Edwin Hubble was a gifted athlete as a youth, leading the University of Chicago's basketball team. After graduating with a science degree, he studied law at Oxford University. Returning from England dressed in a cape and behaving like an aristocrat, he was described by Harlow Shapley as absurdly vain and pompous. Despite his flair for self-publicity, Hubble was a cautious scientist. He described himself as an observer, and reserved judgment until he had sufficient evidence. He reacted furiously if anyone encroached on his field of research. It is to Hubble's discredit, therefore, that he did not acknowledge that 41 of the 46 redshifts used to formulate his famous law were measured not by him but by Vesto Slipher. Hubble spent his last years campaigning for a Nobel Prize to be awarded in astronomy. He died in 1953. Key work. 1929 A relationship between distance and radial velocity among extragalactic nebulae. See also, Measuring the Universe, The Theory of Relativity, Spiral Galaxies, The Birth of the Universe, Space Telescopes, Curtis Arp. In context. Key astronomer. Subramanian Chandrasekhar. Before 1914 Walter Adams details the spectrum of 40 Eridani b, an unusually faint white star. 1922 Dutch astronomer Willem Lutten coins the term white dwarf for low-mass white stellar remnants. 1925 Austrian physicist Wolfgang Pauli formulates the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This leads to recognition of the phenomenon of electron degeneracy pressure. After 1937 Fritz Zwicky characterizes a Type 1a supernova as the explosion of a white dwarf that exceeded its Chandrasekhar limit. 1972 Astronomers find the first stellar black hole candidate. In 1930, a young Indian student named Subramanian Chandrasekhar calculated that a star that ends its life with a little more mass than the Sun cannot hold itself up against the pull of its own gravity. This was key to understanding the life cycles of stars, and in particular the dim, very hot stars called white dwarfs. This type of star was known to be very dense and made of compact, degenerate matter composed of atomic nuclei and free electrons. White dwarfs were prevented from collapsing by a phenomenon known as electron degeneracy pressure. This meant that, when electrons were packed very close together, their movement was limited, creating outward pressure. The Chandrasekhar limit. Chandrasekhar figured out that electron degeneracy pressure can prevent a white dwarf from collapsing only up to an upper limit for the white dwarf's mass, which is about 1/4 times the mass of the Sun. Today, it is known that the core of a giant star at the end of its life will collapse into a white dwarf if its mass is below the Chandrasekhar limit, but will collapse to an even denser object, a neutron star or a black hole, if its mass exceeds the limit. This insight was largely ignored by the scientists of the day because neutron stars and black holes were, at this time, still purely theoretical. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time. Subramanian Chandrasekhar. See also, Discovering White Dwarfs, Nuclear Fusion Within Stars, Supernovae. In context. Key astronomer Karl Jansky. Before 1887 German physicist Heinrich Hertz demonstrates the existence of radio waves. 1901 Italian inventor Guglielmo Marconi sends a radio signal across the Atlantic, unknowingly bouncing the waves off the ionosphere. After 1937 American amateur astronomer Grote Reber makes the first radio survey of the sky. 1965 James Peebles proposes that universal background microwave radio waves are the last remnant of the Big Bang. 1967 Anthony Hewish and Jocelyn Bell Burnell detect a repeating stellar radio signal, the first pulsar. 1998 Sagittarius A is shown to be a supermassive black hole at the center of the Milky Way. While working for Bell Telephone Laboratories in 1930s America, telephone engineer Karl Jansky was given the task of plotting the natural sources of static that might interfere with long-wave radio voice transmissions. To conduct his investigations, Jansky hand-built a directional radio antenna that was 100 feet wide and 20 feet high. The contraption rotated on 4 tires salvaged from an old Model T Ford. His colleagues dubbed the device Jansky's merry-go-round because the young engineer would systematically rotate the antenna to pinpoint sources of atmospheric radio waves. Radio astronomy. Jansky matched most sources of radio waves to approaching thunderstorms, but there was a persistent hiss that remained unidentified. The intensity of this static rose and fell once a day, and initially Jansky thought he was detecting radio from the Sun. However, the brightest spot of radio waves moved through the sky following the sidereal day, not the solar day, and Jansky realized that the radio waves were coming from the constellation Sagittarius. At the heart of the Milky Way, radio waves were shining from space just like visible light. The newspapers reported the discovery of extraterrestrial radio, and astronomers soon began to copy Jansky's device, in effect the first radio telescope. This opened up the possibility of viewing the universe in a new way, not from its light but from its radio emissions. Jansky is pictured here with his hand-built antenna. He published a paper on his work in 1933, but soon after was reassigned by Bell Labs and did no more astronomical work.